Hey everybody, welcome back to chemistry. And so with this presentation, what I want to try to do is describe something called the Born-Haber cycle. And so what that is a detailed description of how a solid ionic compound forms from its constituent elements in their natural states. This can be kind of complicated. And so to explain this, I'm going to first try to make a simplified picture of what's going on here on the left side. And then once that's finished, I'll go into more details here on the right side. And so let's take a look of how the Born-Haber cycle describes in detail the formation of solid sodium chloride from its constituent elements, which are sodium in the solid state and chlorine in the gaseous state. So one thing we want to do is go back to 109 and remind ourselves of an equation that describes this. And so you may recall is that equation is associated with the change of enthalpy of the formation of the ionic compound. But first, let me just write out the equation first. So we're going to be looking at the formation of good old salt, table salt, NaCl solid. And so maybe one of the things you might remember from 109 is I asked you to write an equation that describes its formation from its constituent elements when those elements are at room temperature and room pressure. And so one of the things you might remember is that one of the elements involved is sodium here. So I'm going to write sodium. And that room temperature and pressure, it's in the solid state, so I'm going to write an S there. But then we have chlorine. Now, chlorine is a little odd because, as you may know, chlorine at room temperature and pressure is a gas, and it's gaseous molecules. It's a diatomic molecule. So we can't just write Cl. We have to write Cl2 in the gaseous state. But then you might recall in 109 we had to balance the equation. And so these equations describe the 1 mole of the formation of the compound. So we have to sometimes use fractions over here on the reactant side. And so we have 1 mole sodium chloride here. That balances with 1 mole sodium on the left. But to get the chlorines to balance, we really need a half mole of diatomic chlorine to balance the 1 mole of chlorine atoms on the right. So that is a good balanced equation for what's going on. Okay. So again, what we're going to do is we're going to describe this reaction in very great detail. So maybe you can sort of see at this time some of the problem with describing this reaction, and that there's going to be a lot of individual steps. So let me just kind of give you a quick tour of that. And so one thing that you can see, for example, is that here in its natural state, the reactant chlorine is in a gas, right? But here in the product, chlorine is no longer in the gaseous state, it's in the solid state. And furthermore, it is a single atom, and it's also going to be an ion here. And so you can imagine there are going to be little individual steps to take, for example, chlorine in the gaseous state and get it into chloride ions. And so to really understand all the steps that you're going to go through, what I'm going to do is I'm going to draw pictures of these molecules. That helps us understand the steps we need to go through. But before I do, let me color code the elements here. And so sodium I'm going to code as red, so I'm just going to rewrite this as sodium, solid. And then chlorine, I'm going to color code green, like this. And then we have the product here, which is sodium chloride. And so sodium and chlorine. And this will be in the solid state. Okay, so to understand the steps of this reaction, I'm going to draw some pictures of these molecules. So first, let's focus in on solid sodium chloride. And so you might imagine what that looks like. It's basically alternating sodium chloride ions in three-dimensional space to form a crystal. So we have sodium, but importantly, it's in the form of an ion, so it's going to be positively charged, right? So here's a good old sodium ion. Here's another sodium ion, looks like maybe like this. And then between the sodium ions here, I have a chloride ion. So this is Cl minus. Here's another chloride ion here. And here's another chloride ion here. And then between the chlorides, I have sodium ion like that. So that is a nice picture of what solid sodium chloride looks like. Now, let's compare that to sodium as a reactant. It looks quite a bit different. So one difference I'm hoping you see is that when you have a solid ionic compound, the atoms here are in the form of ions. But here, sodium is not in the form of an ion. It is a neutral atom. And so sodium metal actually looks like this. You have a sodium atom, and there's going to be a metallic bond with another sodium atom, and there's going to be another metallic bond to this sodium atom, and so on. And so again, importantly, sodium here is not ionized. Here in the solid compound it is ionized. Okay, so now let's draw a picture of chlorine. So chlorine here is a diatomic molecule. So we have one chlorine atom here, and it's bound by a covalent bond to this chlorine atom there. So that here is Cl2. And so let me just draw another one. So here we go. This is Cl2. Okay. So our goal is to describe the individual steps by which we take sodium metal and chlorine gas and then convert them into sodium chloride ions that are going to be found in a solid. And so I think you can see there are probably going to be a lot of steps involved. And so let me just kind of walk you through the steps very quickly. So here we have sodium in the form of a solid. And so one of the things you have to do is we have to separate out the sodium atoms into gas atoms. And so we're going to have to add energy eventually. And then so one of the steps early on is just to separate these sodium atoms, and now they're in the gaseous state, like this. All right, that's one step. Okay, we are getting closer to forming the sodium chloride solid compound. So what would be the next step? So here with the sodium atoms, what we have to do is we have to ionize them. So we're going to have to hit them with energy. So we get one electron to leave each sodium atom to produce a sodium ion. So a next step is we're going to add energy, and electrons are going to be flying off the sodium here. And so what you get now is sodium ions here now. Okay, so clearly that's another step that's involved here that gets us closer to the solid sodium chloride. Okay, so that's that. Okay. We'll get back to sodium in a second. Let's kind of focus in now on chlorine. And so chlorine is a little bit different, but still our goal is to take these diatomic chlorine molecules and turn them into monatomic ions. And so we're going to need some steps to do that. So one thing I think you can see is that unlike sodium, which is in the solid state, chlorine at room temperature and pressure is already in the gaseous state, which is what we want. So what we need to do is, the first thing we need to do is we need to add energy to break the chlorine atoms in the molecule. So we separate the chlorine atoms. So we have chlorine atoms like this. So now we got chlorine atoms, but then we need to get chloride ions. And so how do we handle that? Well, what we do is we have a step where we take the electrons that are released by sodium and add them to the chlorine atoms to get chloride ions like this. Now, I think maybe at this point you can start to understand why we need these elements in gaseous form. And the reason is this. You might recognize the process of taking sodium atoms and ionizing them to form sodium ions and electrons as ionization energy. You might recognize the process of taking chlorine atoms here and adding electrons to them to form chloride ions as electron affinity. You might recall that really we can only quantify those when the sodium atoms and the chlorine atoms are in the gas phase. And so that's the reason why we sort of have to convert them to the gas phase. So the good news is this. We have sodium ions in the gas phase, and we have chloride ions in the gas phase. And so all we have to do is bring them together. So I'm going to put a plus sign here to show that we're going to add these together. And then what will happen is when you add them together, they're going to release a lot of energy. That energy I think we talked about before. It's called the lattice energy. And then when you add them together, they release a tremendous amounts of energy, and then you form the solid sodium chloride. And so basically, this is a nice description of how we take two elements in their natural states at room temperature and pressure and get solid ionic compound. You can see that there are several steps involved here. And so what I'm going to do is I'm going to relate these steps in a couple of different ways. And so I'm going to draw an energy diagram, what's going on, and then I'm going to write out some equations as to what is going on. But before I do that, let me enumerate the steps. So the first step here is usually taken as taking solid sodium metal and turning it into a gas. And so when you take a solid and take it directly to a gas, meaning you skip over the liquid phase, you just go from solid to gas, that is called sublimation. So this step is a sublimation. So usually in most textbooks, they say here, taking these chlorine molecules and breaking the bonds between the atoms, that is usually step 2. And so this is a process where you're simply adding energy to these molecules and you're breaking the bonds and you're separating out the atoms, okay? And then usually step 3 is where you take these sodium neutral atoms in the gaseous state and then you pull off electrons by adding energy and get the sodium ions, and so we'll call this step 3. Here next, step 4 is usually where you take the chlorine atoms and you get the electrons from sodium and add them to form chloride ions. So this is step 4. And then finally, adding the ions together to form the salt here is step 5. Okay, so now what I want to do is relate all this information in an energy diagram. And then what I'm going to do is I'm going to write stuff up there. Okay. So the first thing I want to do is I want to talk about how we represent this equation here for the formation of the ionic compound of an energy diagram. So there's a very important fact I need to point out to you is that when you have these elements here, sodium in the solid state and chlorine in the gaseous state, they have relatively high amounts of potential energy. But believe it or not, sodium chloride actually is a more stable compound than the individual elements. If it's more stable, it's going to have less potential energy. So we can represent that here like this on an energy diagram. We have increasing amounts of energy on the y-axis. And so what I have here is I'm showing with a line where the relative potential energy of the sodium and the chlorine reactants are, okay? So it's there, and then you can see that the relative potential energy of the solid sodium chloride is lower. And so maybe one of the things you remember is that you can describe the reaction using changes of enthalpy. And all the change of the enthalpy is just a change of the energy here. So if you want, you can think of the energy axis as being an enthalpy axis. So this is an enthalpy axis, which is represented by H. And here we're just looking at the change of enthalpy of taking elements and taking them and then converting them into a solid salt. And so this is the change of enthalpy for the formation of sodium chloride. So I've written out the reaction here, and then I've just indicated here that this is the enthalpy of formation of sodium chloride. Okay. Our goal is this. I'm going to write out all the steps, 1, 2, 3, 4, 5, in this energy diagram. And our goal is to take here the reactant energies and bring them through the steps and then eventually get down to the energy of the solid sodium chloride. So let's go ahead and go with step 1. So the first step is to take solid sodium and then we're going to sublime it into a gas. And so you can imagine that if you're taking solid sodium, you're going to have to add heat to it to have it sublime into the gaseous state. That means it's absorbing energy. It's an endothermic process. And so what that suggests is that the gaseous sodium atoms have more energy than the solid ones do, right? And so how do we represent that? Well, we say, okay, the gaseous sodium atoms have higher energy. And so what we're going to just here is indicate here, up here in this graph, we have sodium in the gaseous state. Now, we're not doing anything to chlorine yet, so I'm just going to leave that as is, like this, 1/2 Cl2 gas. Okay, so here, this is sort of step one here. So let me draw an arrow going up like that. So this is step one. And what I've already done over here is I have written down an equation that describes step one here. And so again, here I'm just saying the reactant is solid sodium and returning into gaseous sodium. And so we can describe this with an enthalpy change of the reaction for step one. And so I'm just indicating here is this is also the enthalpy change for the sublimation of sodium. Okay, so now let's move on to step two. So now we're going to deal with chlorine. And so here what we're doing is we're taking molecules and busting the covalent bond between the atoms. And one of the things you probably have learned is that you require energy to break the bond between the atoms. And so that suggests to you that when you're adding energy to break the bonds, the atoms are going to have to take that energy and absorb it. And so you get individual atoms like this. And so here, what I'm going to do now is I'm going to indicate here that now we're at chlorine atoms which have higher energy than the chlorine molecules because we had to add energy in them to break the bonds. And so to represent chlorine now as atoms, we just write Cl. Okay, so maybe you can see why. Here we have Cl2, so here are the individual chlorine molecules. And we had to write a 1/2 here just to balance the equation, but really just kind of focus on the fact that these are diatomic molecules. And when you bust diatomic molecules, you get atoms. And so needless to say, if you have a diatomic molecule, you'll get 2 chlorine atoms, but if you have half that, then you'll just get chlorine atoms. So you just have a 1 there in front of the chlorine. Okay, so this is in the gaseous state. We haven't done anything to sodium right now, so this is still sodium in the gaseous state. So here, this is step 2. Okay, and so let's write out an equation that describes step 2. And so it's going to be 1/2 Cl2 in the gaseous state is going to give you Cl atoms in the gaseous state. And so this is step 2, and this is a change of the enthalpy is associated with this change. And so if you want to call this, you can call this the change of the enthalpy associated with the bond energy of diatomic chlorine. Okay, so what you can see is so far, what we're doing is basically we're just adding more energy into these elements and they're changing into new forms. And so we're going to kind of continue on this process. And so step 3 is kind of interesting. Here we're taking neutral sodium atoms in the gas phase, and what we're going to do is we're going to ionize them. And so you may recall how we do that. It's through a process called ionization energy, and so we hit the gaseous sodium atoms with a lot of energy, and then the electrons fly off, and you get these sodium ions here, okay? So this is step 3, and so here we're going to have to add energy to the sodium atoms, they become ions, and so the sodium ions are going to have higher energy still, so we're way up here now. And so here we have sodium ions here. They're in the gaseous state. Chlorine is still in atoms. We haven't done anything with that step yet. That's fine. Okay. And so step 3, again, is an endothermic process. We have to throw in a lot of energy to get the electrons off sodium. Okay. So let me write that out. This is kind of an important step. So here we have neutral sodium atoms in the gaseous state. And then we're going to add energy to them. And I'm leaving out energy terms in this just to make my life easier. And so you're going to get sodium ions now in the gaseous state, and you're going to get electrons. Okay, and so this is step 3. So this is delta H3. And you can call this the change of the enthalpy for the ionization energy of sodium if you want. That'll be fine. Okay, so let's now go to step 4, which is also an interesting step. And so in step 4, we're going to take these chlorine atoms here, and what we're going to do is we're going to add electrons to them to get chloride ions. But here's where it gets a little bit interesting. And so let's reflect back on the energy changes in ionization energy and electron affinity. So you might recall with ionization energy, what we do is we add energy to the atoms to ionize them. And so that is an endothermic process. But you may recall with chlorine, when we add electrons to the chlorine atoms so that they become chloride ions here, that is actually going to release energy into the environment. That's actually an exothermic process. If that is the case, the resulting system, after you take the electrons and add them to the chloride, is going to have less energy than it did when you had neutral chlorine atoms. And so we're really here now for this next step here. So I guess I could have put the line here, but just to make it less confusing, I'm just kind of moving it out here so that we can see it a little bit better. Okay, so let's describe what we have when we add electrons to chlorine to get chloride. So what we have here now is we have chloride ions, and again, they are lower in energy than the chlorine atoms. And then we have sodium ions still. And then remarkably, here the energy falls for the system. So this is step 4. And again, this is a property of electron affinity. When you add electrons to an atom like chlorine to form chloride, that is where the chloride ions will become more stable than the chlorine atoms, and they're going to release energy. Okay, so let's write out an equation describing the electron affinity of chlorine. So we have chlorine in the gaseous state, and we're going to add an electron to it, and we're going to get the chloride ion in the gaseous state. And so this is step 4. So one way to designate this is the change of enthalpy of step 4, or change of enthalpy associated with the electron affinity of chlorine atoms. Okay, so now there's a final step. And so the final step is where you take sodium ions and chloride ions in the gas phase and you just bring them together. And when you bring them together and they start binding together to form the solid sodium chloride salt, that releases a tremendous amount of energy. And so, in fact, that energy has a name associated with it you learn about. It's called lattice energy. And lattice energies will be exothermic. And here you can see it's exothermic by quite a bit. So this is step 5. And so let me write out this process here, in that we have sodium ions in the gas phase, and we're going to add that to chloride ions in the gas phase, and we're going to get solid sodium chloride salt. And again, this is step 5. And then we have a change of enthalpy associated with step 5. And this can be thought of as the change of enthalpy for the lattice energy. I'll just write E for sodium chloride. Okay. So what I want to do at this point is I want to write a basic equation that shows you that you can sum step 1, 2, 3, 4, 5 and get here the change of enthalpy of formation of sodium chloride. In other words, this original reaction here. So I'm going to erase this here. Okay, so this was the original reaction we were looking at. And our goal was to take this reaction, which is a description of the formation of the ionic salt sodium chloride from its constituent elements, and then just break it down into the steps. And so what you can see of this energy diagram is that here all the energy steps, when added together, should be equal to this, the change of the enthalpy for this reaction here. So this reaction, again, can be described by change of enthalpy, which is delta HF formation of NaCl. And what I'm kind of hoping you can sort of see is we can add the enthalpies of the individual steps, and we should be able to get that. So the enthalpy of step 1 plus the enthalpy of step 2 plus the enthalpy of step 3 plus the enthalpy of step 4 plus the enthalpy of step 5 should be equal to the change of enthalpy of the formation of sodium chloride. One of the things that's important to keep in mind is that chemists oftentimes cannot directly measure the lattice energy of bringing ions together to form an ionic solid salt, but they can measure everything else. In other words, they can measure maybe some of these individual steps, and then they can measure the enthalpy of formation of the compound from its elements. And so is there a way that you can sort of calculate what the lattice energy is for a particular ionic compound, given that you know everything else? And the answer is yes. So if you're trying to find lattice energy, this is the one you're trying to find, the change of enthalpy number 5 here, right? And so let me again just mention here that this is lattice energy. And so I think you can sort of see now that lattice energy can be calculated if you know the energies with the individual steps and also for the enthalpy change of the formation of the compound. So I think you'd see that here the lattice energy, which is the change of enthalpy for step 5, is going to be equal to the change of enthalpy for the formation of sodium chloride minus all these other steps energies added together. So what we're going to do with the next presentation is we're going to actually do some problems where we actually calculate lattice energies for ionic compounds, given that we know all the other steps. We're going to do it in a way that I think is more rigorous. We're going to use something called Hess's law. So we will see you next time for that.